Good morning. We have been discussing pile foundations and we started off saying what pile foundations are and which are the cases where you'll have to resort to pile foundations, which are the different types or classifications of piles, etc. Later on we moved to the determination or estimation of pile load capacity, and we started off saying that you can have four different methods. One is a static method, second is a dynamic equations, third is in situ penetration test, and fourth is a pile load test. Now, later on, we briefly stepped on to what static method means. We discussed QU is equal to QP plus QS, capital QU being the ultimate load from top, QP, capital QP, being the tip resistance in kilonewton, QS, capital QS, being the skin friction taken in kilonewton. Then we discuss what bearing capacity small letter QP is influencing capital letter QP. QP into AP is equal to capital QP. And later on we've discussed what FS into AS contributes to capital QS. So in short, the entire load that's acting on a pile foundation can be taken by end bearing or skin friction or both. Like we discussed in the previous video, you can have pure end bearing and pure friction, but that's very rare. So every pile installation in field is expected to have the load transferred or shared by end bearing and friction combined in different variations, of course. Now, we later on discuss what Fs is. In case of sand, Fs is equal to K sigma V tan delta, as you can see in this equation. And in case of clay, you can have alpha into C, where alpha is the adhesion or the reduction factor for adhesion. C is the cohesion in kilonewton per meter square. Sigma V, in case of sand, is the effective vertical stress at the mid depth of the pile. Delta is the angle of interface friction between the concrete and sand. K, of course, is the lateral head pressure coefficient. Now, as you can see in this picture, the total load from the superstructure is partly shared by friction and end bearing, but in this particular case, it kind of represents the friction pile or skin friction pile, where the pile is not extended up to the rock level. Instead, it's curtailed somewhere above, which means you can't expect much of a share taken by the end bearing load. Instead, the load is predominantly taken by skin friction. So I used to take an analogy in the classroom where you can hold a pen onto a table vertically, and in that case, that's end bearing because the pen rests on the table at its tip, so that's end bearing. Whereas when you hold the pen on your hand, on your gripping the pen, that's skin friction. Quite similar to that, you can have the pile foundations constructed in field, either to take end bearing or friction or both. Now, when you discuss K sigma V tan delta term, you can see that sigma V is proportional to Fs, or to be precise, Fs is proportional to sigma V from this equation, which means it linearly increases, or when sigma V increases, Fs increases. But sigma V, by definition, is effective vertical stress at mid-depth of the pile. So this equation signals that as you go deeper, as a pile is installed deeper, you'll have huge values of Fs. But that is not the case actually. Of course, there are arguments whether it is the case or not, but still, there comes a picture, critical depth for sigma V of sand. There's a theory which says that the effective vertical stress need not increase with the depth, or sigma V need not increase with the depth. Sigma V, as we are all familiar with, is nothing but gamma into h, or unit weight multiplied by height. In this case, unit weight multiplied by length of the pile. So the critical depth theory says that sigma V need not increase linearly with respect to the depth. Instead, it can increase up to a certain depth called as a critical depth, and later on it can remain, or it should remain, constant. So it linearly increases to a depth what we call as a critical depth. Sigma v increases up to that value, and later on it remains the same. In short, sigma v is not purely triangle like this as you expect from the equation. Instead, it's a combination of a triangle and subsequently a rectangle. Of course, it's a bit confusing to those who think deeper into the subject. Nonetheless, critical depth states that up to a certain depth of pile, the effective stress increases with depth, and later on it remains constant. Now this depth, what I've marked as LC, the critical depth, is or can be taken as 10 times the diameter for loose sand and 20 times the diameter for the dense sand. This is just an approximate method to estimate LC, or critical depth. There are detailed equations to arrive at the critical depth, but for your graduate level, you can imagine that the critical depth is 10 times the diameter for loose sand and 20 times the diameter for dense sand, d being the pile diameter. Again, to take an example, let's say that you have a pile of 0.5 meter diameter. So let's assume that it is installed in loose sand. So critical depth is 10 times 0.5, that's 5 meter. 5 meter here. Let's assume that the pile is actually 10 meter long. So the pile is 10 meter long and the critical depth is just 5 meter, which means the stress sigma v increases up to 5 meter and later on remains constant for the rest of the 10 meters that's left behind. So you have 5 here and you have another 5 here. So that's what the critical depth says. Of course, there are arguments. I used to say again in the classroom when we used to have discussions, it's quite similar to a debate whether God exists or not, whether the aliens have landed here on Earth, whether humans have landed on the moon. So these are topics of debates. Quite similar to that, critical depth is a topic of debate. A few textbooks tend to follow that there exists critical depth, and a few other textbooks argues that there's no critical depth. But for a design engineer, it's always safe to assume that there is critical depth. So it's a conservative design, it's a safe design to assume that there's a critical depth. Or else if you don't take a critical depth, you will have a huge value of Fs, and hence you'll have a huge value of pile capacity, which may not be the actual case in field. So it's to be on the safer side, it's good to take the critical depth. Anyways, next we have a term called as a negative skin friction. Negative skin friction is described in this figure. Let's assume that you have the pile again installed up to 10 meter. Q is the total load acting on it, a part of which is shared as point resistance and a part is shared as skin friction. Now if this pile of 10 meter length is installed in natural stiff soil, the soil will offer resistance against its downward motion, which means when the pile is acted upon by load from top to bottom or axially compressed, the soil will offer resistance upward, which is nothing but the skin friction. So the soil tends to hold the pile upward. That is a case where you have a natural soil fill. But let's take a case where for a depth of LC, again, for example, let's take that as 2 meter. 2 meter from the top, the soil is not natural, but it's filled up soil. It's in a loose state. So if such a case exists, when the pile is acted upon by load, the filled soil, instead of resisting the pile movement, acts along the pile's movement and offer a downward drag, for the simple reason that the soil is not strong enough or stiff enough to hold the movement of the pile, so it fails and it moves along with the pile in the downward direction. Had it been the natural stiff soil, it would have offered a resistance, but in this case, if it's a filled soil, it doesn't offer a resistance and it moves along with the pile downward, causing a downward drag onto the pile, which of course is an extra load that the pile has to take. So it's a burden for the pile. Now what is negative skin friction? It is when the soil surrounding the pile shaft exert a downward drag. When and why? When the soil around the portion settles more than the pile, or in case of a soft or loose soil, when the relative movement between the pile and soil exists. The result is that it reduces the ultimate capacity of the pile. Had it been the natural soil, it would have offered a resistance, but in our case it's negative skin friction, so it's a burden, so it reduces the ultimate capacity of the pile. Now, how to overcome that? In practice, we provide a protective sleeve or a coating onto the pile. So wherever there's a portion where you can expect to fill soil, where you can expect negative skin friction, you provide a protective sleeve or a coating onto the pile so that the negative skin friction is reduced.